So ultimately, you have to understand what exactly the basic concept is. Okay? See, I told you, you may be thinking that I am repeating this every time, but see that what we are doing to generate double sideband suppressed carrier wave. What you get here is m of t into cos of omega ct. And what is this? Double sideband suppressed carrier AM wave. Never forget this. Right? Okay. Now what we did in that analog, that is variable, variable gain transistor amplifier circuit which you have seen, we are trying to implement this. This is a multiplier. Of course, we have written it as a common multiplier, general multiplier. Okay. But actually, when it comes to the hardware, this is going to be your electronic device. This is going to be your electronic circuits. Right. So we have to get something called as multiplier modulator. This is called as multiplier modulator. That's what we have seen. The first method, which is this variable gain amplifier, and part of that is nonlinear modulator. This is nonlinear modulator. This is an adder, and this nonlinear device is nothing but your diode and transistor. And this is an adder. And what you get here from m of t and cos omega ct at this point is this one. Right? Now, out of this, what is your AM wave? This one, right? You have to remove this. This is the baseband component, this is the passband component. To keep passband component, you have to use a band pass filter. That's all. So what you do is, you use a band pass filter here, and what you are going to get is, and this is that multiplier which I have used here. Have you understood this now? Okay. Now, second method is called as switching modulator. Switching modulator. That same multiplication operation which I have told you is replaced by a switching modulator. What is the switching modulator? It's very simple. It's very simple. Now, see how this switching modulator will give you AM wave. Right? Keep it in mind, your AM wave is nothing but m of t into cos omega ct. Keep it in mind. That's what expression you are supposed to get. And how do you get that expression? Just by multiplying your message signal with the periodic signal. Just multiplication. Right? Just multiply your m of t by any periodic signal phi of t of the fundamental radian frequency omega c. Right? So let that periodic signal phi of t is equal to summation from n is equal to 0 to infinity Cn cos n omega ct plus theta n, where theta n is the phase of this. Can you tell me, I want you to now ask one question. Can you tell me what is this representation? What is this representation? Come on, I told you in my previous class. You must be able to answer my question now. What is this? Fourier series, exactly. See, moment your periodic signal comes into existence, to represent a periodic signal, you can use Fourier series method. The Fourier series representation. Why Fourier series representation is there? If you want to mathematically write your periodic wave, only way you represent is Fourier series. Fourier series. That's why I am writing a periodic signal, okay, as a phi of t, which is the periodic signal. It is represented as in the form of Fourier series. Now I said it is possible to generate an double sideband suppressed carrier wave. Okay, it is possible to represent this multiplier nothing but as multiplying your message signal, okay, multiplying your message signal with the periodic signal. I am just multiplying it. I am just multiplying a message signal with the periodic signal, and I can represent the periodic signal as my Fourier series expansion. Okay, now just multiply. So this is your phi of t, okay, this is your phi of t, this is your phi of t, multiply phi of t with the m of t. Fine. Multiply phi of t with the m of t. Just see this, okay. Now see this expression. See this expression. Can you expand this expression? Can you expand this expression for n is equal to 0 to infinity? Of course, you cannot go till 0 to infinity, but you can go till some, right? Yes or no? Okay. Now, can you expand this? M of t into phi of t is equal to m of t into phi of t is equal to, let us expand, C0 m of t cos of 0, right? Assume that phase shift is 0 for time being. Assume that phase shift is 0. Assume that this phase shift theta n is equal to 0. And when you expand this, what will be the first term for n is equal to 0? It will be what? C0 into m of t plus C1 into m of t into cos of omega ct. Now you have to tell me which term is required and which other terms are not required, okay, to get an EM wave, double sideband suppressed carrier EM wave. You can easily get it out of this equation. What is the next term? C2 m of t, come on. Which one? I said this is the phase shift. We will assume this phase shift to be equal to 0 while expanding it. Right, okay, can just expand it now. This will be m of t into cos of, come on, 2 omega ct, right? Plus, come on, next, dash 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 till infinity it goes. Now tell me, in this entire equation, tell me which is the term required? Which term represents your double sideband suppressed carrier EM wave? Which term? Just check. Is it only except first term? I want answer from you. First term, second term, third term, fourth term, and the lot of terms. Which is your EM wave, double sideband suppressed carrier EM wave in that? Which one? Which term is that? Come on. Huh? Which term is your double sideband suppressed carrier wave? Just now I told you.
The first one.
Is it the first one? Is it your EM wave? No. This one? Is it your EM wave? Yes. Why this is not your EM wave? Because 2 omega c, then 3 omega c, 4 omega c. Right? That means this particular equation, if you just expand it till infinity, will have a baseband component, will have your required EM wave, and these are all not required because here you have 2 omega c. What you require is just, this is your m of t. I am repeating every time, cos omega ct. So what you require is only m of t into cos omega ct. This is what your DSBSC EM wave. I told you that using switching modulator you can generate it. So switching modulator is nothing but you multiply your message signal with a periodic signal, with a periodic waveform phi of t of the fundamental radiant frequency omega c. Now when you multiply this, okay, by using Fourier transform, Fourier series representation of the periodic signal, you get this equation, right? So in this equation, you have clearly seen that this is the only component required. Is the passband component, right? That means once you just multiply this, okay, you are actually passing it through a band pass filter. Right? If you pass this through a band pass filter with the cutoff frequency, okay, what is the cutoff frequency? Suppose if your baseband frequency is B, right? So you need only, what is the passband you require? You just require from Fc minus B to Fc plus B. Only this is required, right, for you. So you just try to have a band pass filter with lower cutoff Fc minus B and upper cutoff Fc plus B. That's what your sideband is. And remove all other component. If you use a band pass filter with the cutoff frequency lower cutoff Fc minus Fb, Fc plus Fb, only this particular component will be moved. Have you understood this? Only this particular component will be passed. All remaining components will not be passed. It will be suppressed. Have you understood this? Okay? This is called as filter. I think by looking at your face, I can make out you don't know about concept of filter. Do you know concept of filter? How do you see this filter operation from frequency domain point of view? Do you know it? How do you see a filter? How you will filter a signal, okay, in a frequency domain? Listen carefully, okay? This is very important. You are supposed to know this in signals and systems. I am just repeating once again here. See, unless you understand this, I don't want to simply pass on my slides. Your understanding is very important for me. See here, normally filters in frequency domain can be seen from its filter transfer function. Right, see here, see carefully here. This is your F, okay, I'll write F, it can be omega also. Right, okay. Now, see here, this is your H of F, I'll write H of F, capital H of F, frequency domain, okay. Now, I will write this amplitude 1 here. Similarly, I will write, okay, this is your Fc, this is your minus Fc, this is a band pass filter. This is the frequency response or transfer function of a band pass filter. Right, okay. Now, while filtering in the frequency domain, we simply multiply, right? We simply multiply, yes or no, right? Now, see here, this is your B, this is your B, okay? This is a band pass filter with the center frequency FC and with the bandwidth of 2B, right? This is also B, this is also B. That means this is FC minus FB, this will be FC plus FB, yes or no? If this is 2B, okay, so this will be FC minus FB, this will be FC plus FB, yes or no? It's quite obvious from here, all of you can understand this, right? Okay. Now, the spectrum which you are talking about, right? You have the signal, right? See, you have this m of t multiplied by phi of t, right? It is actually summation n is equal to 0 to infinity Cn m of t into, what is that? Cos of, come on, n omega c, right? I am just writing it in omega c, okay? It can be even in 2 pi fc also, okay? If you are getting confused, I will change everything to omega c, okay? So in that case, this will change to what? This will change to omega. Can you tell me what are the changes going to happen here? Come on. This will be omega c, right? This will be omega c plus, if I say it as a B hertz, so how do you convert it into omega? 2 pi b, right? 2 pi b. This will be 2 pi b. This will be omega c minus 2 pi b, okay? Accordingly, you change this. Have you understood this? Okay. Now see here. Listen carefully. Listen carefully. So n omega c plus theta n, right? Yes or no? Into t. Into t is there, na? T is there. Omega ct into, right? Okay. Now, I told you to expand this, right? Now, when I expand this, it will become C0 into m of t, because cos of n, assume your theta n phase shift to be equal to 0, okay, for this cos term, plus, you understood why I am not having cos term here, cos 0, right? Now, next you have C1 m of t cos of omega ct, fine, plus C2 m of t cos of 2 omega ct, fine. Now, plus C3 m of t cos of 3 omega ct, yes or no? Plus dash 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 Cn m of t cos of n omega ct, right? Now, can you draw the spectrum of this? Suppose if the spectrum of m of t, right, if this is your m of t, okay, this is your m of t, spectrum of m of t, for example, this is omega, this is 2 pi b, this is minus 2 pi b. Suppose this is the spectrum, this is m of f. Assume this is to be m of f. Right. Now, see here, this is very important to understand. If you understand this concept, you can understand anything in communication systems. These are Fourier transform pairs. Now, using that, can you draw the spectrum of now? Suppose if I take this 0. Can you draw the spectrum of this? Okay, what is the spectrum of this? C0 into, What is it? Convert it to Fourier domain. M of f. Can you tell me, I told you, what is the frequency domain representation of this? What is the Fourier transform of this? M of f. Okay, I'll go for omega. I'll go omega, okay? Not f, omega. Right? This is m of omega. I'm going for omega now, okay? Because everything is in omega. Fine. Now, what is the spectrum of this? M of omega minus omega c plus m of omega plus omega c, yes or no? Right? Now, can you tell me, how do you draw the spectrum of this m of f? As it is, right? I will just write this as it is, same m of f only. This is 2 pi b, this is minus 2 pi b. Plus this one, right? Now what is this one? Shifting, right? This is shifted by omega c, shifted by minus omega c, yes or no? So same, I will have one here, shifted by omega c here, shifted by minus omega c here. Same thing. And what is this? This is omega c plus 2 pi b. This is omega c minus 2 pi b. Okay, next, is it over now? No, what about this term? Same thing, shifted by 2 omega c. You will have one more here at 2 omega c, same thing. This is 2 omega c plus 2 pi b. This is 2 omega c minus 2 pi b. Understood this? Same here also. Now this will continue, right? This will continue. The spectrum, this spectrum will continue for 3 omega c, 4 omega c, 5 omega c and so on. Now you tell me, in this entire term, which are the two are the required one? Which are the two spectrum represents your double sideband suppressed carrier wave? This one and this one, right? You don't need this. You don't need this. You don't need this. You don't need anything. To get that, you are passing it through a band pass filter. This is the band pass filter. Band pass filter in frequency domain, just multiplication. When you multiply this and this, can you tell me what will remain? See, this is 1, is all 0. See, when you multiply this is all 0 here. When you multiply these two, tell me, what will remain? Only this will remain, right? Only this will remain. And what is this multiplication process? That is filtering. And this is actually band pass filter. Yes or no? This is band pass filter. So you are going to multiply this with the band pass filter. Okay? Now which component will remain? Only this component. That means only this component will remain. All these components, all these components will go. And that is nothing but your double sideband suppressed carrier wave. I told you, this is the replica of that. It's not two band pass filter. Whenever you draw a band pass filter in frequency domain, whatever is there this side, same thing will come this side. This is because of the symmetry property. Right? Drawing only one-sided is not correct when you draw the Fourier transform. Other side also will be there because of symmetric property. Have you understood this? Okay? Most of the students have this, still they have the doubt. Sir, why you are drawn here? Is there a negative frequency? No. It is just a symmetric part of this. Have you understood this? Whenever you draw a Fourier spectrum, you draw like this. Always. Have you understood this? Okay, this is very important. Okay? Now, see, ultimately, just by multiplying a periodic waveform, we got double sideband suppressed carrier wave, yes or no? Yes or no? Right? That is what this switching modulator is. That's what switching modulator is. See, I will take now one switching modulator case. See, I have already explained you this. Okay, I have already explained you this. Now, let us consider a periodic pulse train. Let us consider a periodic pulse train, right? We have proved that multiplying a periodic wave with the frequency omega c, okay, to the message signal will get you the double sideband suppressed carrier wave. We have proved it mathematically, right? Now, let us consider that periodic wave as a square wave pulse train, right? Now, I hope that you are able to apply Fourier series for this and represent this signal in the form of Fourier series. Yes or no? You can do it, right? Fourier series expansion. This is what in signals and systems you are studying, right? Now, I have already done it. So, I can represent the square pulse train. See, square pulse train. This is a square pulse train. The Fourier series expansion of this square pulse train, I have calculated already, is given by this. This is the Fourier series expansion of the square pulse train. Okay, now what is the next work for me? Multiply this with the message signal. Multiply this with the message signal. See what you will get? You will get this series, right? Yes or no? Multiplying this with the message signal, you will get this. See, listen carefully. Okay, now tell me now, what is my next work? You have to tell me now. Once I multiply it, what I should do next? You will get this. This equation has something which is required, something which is not required. So how do you remove that? Use a filter, right? Use a band pass filter with the cutoff frequency, with the center frequency omega c, and all other frequencies, center frequencies are not required for us. So you just have to pass this. This is not required. This is not required. This is not required. What is required is only this. So you pass it through a band pass filter with the center frequency omega c, So what you get is only this term. What is this term? Come on. Double sideband suppressed carrier wave only. That's all. Right. So in this way, you can generate a double sideband suppressed carrier wave. See, this is what I have told you. See. This is your M of t, this is M of f, okay? And you see this is your W of t. Now you see, you are going to multiply this M of t into W of t, right? When you multiply M of t into W of t, okay, in the frequency domain you see, you get this. Yes or no? Baseband component, first harmonic, second harmonic, third harmonic. So what you require is only these two, yes or no? This is the, of course, while drawing I have made amplitude same, but it won't be because that C0, C1, C2 and all there, right? Okay, that's why. But here that C0, C1, C2 is considered, and you can see the amplitude is going down here. After that you pass it through a band pass filter. So what you get is the double sideband suppressed carrier wave. This is an EM wave. It's an EM wave. Now how do you, can you tell me, how do you get this waveform? How do you get this on off? This is nothing but on off, right? Right. This is on off, on off, on off, on off. Which device gives you that switching action? Diode. Diode. Diode gives switching action. Right. Positive half cycle it is on, negative half cycle it is off. Once again positive half cycle it is on, negative half cycle it is off. Is it not switching action? Right. So when it is implemented in hardware, what we have is simple diode circuit, simple diode circuit. I will come back to that now. Theoretically we have proved, now practically we will see in the modulators. See here, that's what I have told you, this circuit. See this circuit. See here, this is the one which generates your square train pulse. What is the frequency it generates? Omega c. This generates your square, that's periodic signal, right? Did you come across with this type of circuit? You are in third year now. What is this actually? Bridge, Wheatstone bridge, right? Okay. So now, can you tell me, suppose if cos omega ct is, AC cos omega ct, can you draw the AC cos omega ct? Suppose if this is your AC cos omega ct, this is your AC cos omega ct. Okay, of course, I have to draw little abrupt signal. Why I should draw a abrupt signal here? To represent high frequency, right? If I draw like this may be message signal. High frequency is basically, it looks like this. Just to see the switching action, I have drawn this. Otherwise, you will not. High frequency means it will be like this, something like this. Okay, same amplitude. Okay, but I will just try to zoom it and show you what happens to these diodes and all. You have to tell me now. It's quite easy. Suppose this is your A. Okay, so this is signal is A cos omega ct. Frequency of this is supposed to be angular frequency is omega c. Now tell me what will happen at the point A and B during positive half cycle. What type of waveform you get? Assume during positive half cycle, this will be positive, this will be negative, right? What will happen? Tell me. Which are all the diodes gets forward biased? Which are all the diodes get reverse biased? So you will continuously get your a negative and positive amplitudes, right? Yes or no? So this will be forward biased, right? This will be reverse biased, right? During next cycle, other two will be forward reverse biased. So you will get something called as a square wave. We will get both positive and negative amplitudes, which represents your on and off condition. On and off, on and off. Have you understood this? Okay. Now, see, this is your message signal, and this A and B will come here. A and B will come here. And this is going to generate this W of t. That's square wave train. It need not be only a pulse train, it can be square wave train also. Then after that you pass it through a band pass filter, what you get is k into m of t into omega ct. Have you understood this? Okay, now I am going to give you one small homework. For this input, okay, for this input, just find out what is the waveform you get across these 2 points. Exactly what you get. You have to get something like this. Right, you have to get that. And if you represent this in the form of Fourier series, right? How do you convert this signal into a pulse? Just scale it, right? Just scale it. Right, this will go and sit here. You will get a pulse train, and that is nothing but your pulse train, and you have the Fourier series representation of the pulse train. So that is getting multiplied here, right? Okay, and then pass it through a band pass filter. Definitely, you will get only the term k into m of t cos omega c t. Remaining part of this we will do it in the next class. Fine, okay, we will do remaining part in the next class.